Okay, hello everyone. The problem that we're looking at today is none, as you can see, because I do not have enough time, and this will just be a quick review over the stuff I did today. So first of all, the first problem I did was this logo problem of truck transportation, which is actually quite classic. I bet a lot of you guys have done this if you've ever done the minimum spanning tree of Crucial or the LCA algorithm. So essentially, what you're given is you have a bunch of cities, and okay, you just have a bunch of nodes and a bunch of edges, and you're trying to determine the minimum edge. uh you are trying to maximize the value of the minimum edge between uh there's q queries, and for each query there's a pair of point xy, and trying to maximize the minimum edge that is walked through in this between x and y, and you're trying to find that maximized minimum value on this path. So to achieve this, obviously, if you know Crucial, the minimum spanning tree is basically the opposite operation, whereas the maximum spanning tree, and you just choose the n minus one biggest edges, and all those edges make this whole thing a tree, and then, well, I mean, unless it's not connected, and then you just run the LCA algorithm on it. However, you have to make a slight modification to the LCA, which is what I did here. Not only do you have the F array for where this point will get to after I 2 to the ith power jumps, but also what is the minimum value of the path from x to the nodes that is 2 to the ith power higher than x. You can just understand it from this formula basically, and then it's just really easy from that on. You just do the thing with LCA, except you also maintain a running minimum, and that's the answer. So really simple Crucial plus LCA. Second problem I did was a lot harder. It's also a binary lifting algorithm. However, this time it's not LCA, but rather the ST table algorithm, or the RMQ question. If you know what the range minimum slash maximum query is, that's the RMQ. And basically, for this problem, you are given a super piano, and then for each key, okay, this problem is a little bit more complicated, but you can choose to read through this problem yourself or just go on this website. And then basically what my solution was is for each okay, let's see. First of all, you notice that you would always want to fix a left end and try to find the optimal right end by maintaining an ST table on a prefix sum. And if you understand what that means, you basically just, for each left end, you push the best right end into a priority queue, and then for each time you pop an element out from the priority queue, you add 2 back in, and that's the optimal right end for this region on the left side of this right end, and the optimal right end to the right side of this current right end. However, we do not include this current right end so that we don't count it twice. So it's r minus 1 and r plus 1, so we do not count duplicated. And the final problem is the most difficult one, and it's the canon. And I think this one's translated quite well, so you can just try to read it yourself. And the problem statement is really hard to explain if I try to explain it to you. And the spacing is completely off with Google Translate, but whatever. Okay, so basically this one is a classic DP problem, and is quite big brain. Basically, fi equals the number of ways to choose I sets legally, and we notice that after choosing the first I minus 1 sets, well, the I1 must be set, because we know that each node must appear exactly even number of times, and since each of the sets are, well, obviously not a multi-set, but a set, so each of them must only appear once or 0 times. And since we already know the parity of the number of occurrences of the first of each of the n elements in the first I minus 1 sets, we can choose the ith sets accordingly, and we have to choose the ith set accordingly. So now we know how to do that. We still have to count the case where we might choose an empty set, and that is the case where the first I minus 1 is already legal. So we have to subtract that whatever value we just calculated above. It'll be 2 to the nth power minus 1, choose I minus 1. That's the number of ways to arbitrarily choose the first I minus 1 sets, minus fi minus 1, because that's the number of ways to choose these I minus 1 sets such that they are legal, which is something we don't want, because if they're already legal, then, well, the ith one is an empty set, which is not legal. And then the whole thing for duplicates above is, this is a bit more complicated, but you can just try to read through that section yourself. And the conclusion is basically I minus 1 times fi minus 2, and then times this thing. And the code itself is actually really, really simple. Oh yeah, and I just brain farted. Okay, I do not have any more time, and I hope this video helped. Okay, actually, it would not help at all. It's just three completely unrelated problems, and I didn't even explain it very well. But well, here's the grand report for today. Thank you for watching, and I'll see you tomorrow.